Hey, what's going on guys, Kenzie here. In this video we're going to learn how to add two 16-bit numbers in 6502 assembly. So here I have a Q1 emulator, which is probably the kind of simplest possible 6502 based machine, and I'm currently in a serial mode so that we can have a benefit of printing the numbers to the kind of emulated serial port, let's say. And here we can write a code in 6502 assembly, assemble it, and upload to whatever memory address that we like. So without further ado, let's get started. And the very first thing to understand before diving into the 16-bit number addition is this status register layout. So you obviously know that there is a register like a emulator, X and Y registers in the 6502 CPU, but also there is so-called status register full of various flags. So if it comes to the arithmetic operations like adding and subtracting numbers, it's about add with carry and subtract with carry. So this means add two numbers plus the carry flag, or subtract two numbers minus the carry flag. So what is this carry flag? What is this all about? What is this carry flag all about? So we have 1, 2, 3, 4, 5, 6, 7, 8 bits in this register. So you can think of them like this is like leftmost and this is the rightmost, for instance. It's like how I observe them there, definitely. So the idea is that the rightmost bit, if it's set to 1, then it is being added as 1 to the number when you're performing this add with carry, or in case of subtraction it would be subtracted. So before actually considering either addition or subtraction, first usually people kind of clearing the carry flag if they want to add, and setting the carry flag if they want to subtract. So that's kind of how this usually happens. So probably let's go to a little bit of a demonstration. So by default there is a memory location of I can actually show you this in the serial monitor as well. So 00 F1 yes, F1, F2. Yeah, so in the F1 we have what currently we have in the status register. From how do I know this? Well, this is because that's the machine connects, which is save, restore. Well, you just stop or go. So for instance, if I go to 0200 and run, and I just break because there is a 0 at that address. So I just break, and if I have a look at 00 F1 again, still nothing there, right? So, but let's say we just set the carry flag, right? So have the only instructions. So I say set the carry flag, and I want to assemble this at the offset of 200s, okay, and upload and go into 200s. Now we have this opcode for set carry flag, right, and Shift G. And now if I go to F1, then we already have actually two flags being set to the first. So in order to decode this value, so here I just did some decoding stuff. So 3 in binary, this is going to be 0011, and 1 is going to be 0001. So we have so negative is 0, overflow is 0, then the expansion flag, not sure what that means, but actually it's being set to 1 for some reason. Then the break flag is set to 1 because we just encountered the break instruction, so that's important. And then decimal mode flag is equal to 0, but by the way, it's usually a good idea to set it to 0 explicitly, because on the emulator by default it's not set, but on the real hardware it might be. So should have actually say CLD first, but anyway, now it's not the case really. I just want to show you how the carry flag works. Then interrupt flag is 0, interrupt flag is 0, 0 flag is 0, so it's not active, but the carry flag, the very last one here, it has been set to 1. So this is important because this number actually, this single bit actually takes part in either addition or subtraction. So now let's consider the following scenarios. So say we have the carry flag being set here. So I just leave it like so, for instance, or I can even let's make it like this. And let's say LZA, so load some value, like say hexadecimal 10, for instance, to the A register, and say add with carry the constant of 1. So this would be this should result in hexadecimal 11. However, because we already have 1 in the carry flag, it would actually result in hexadecimal 12, because we would also add add that carry as well. So just to demonstrate you this, so if I assemble this again at 200s and upload and go into 200s and run, in order to see the result is now stored in the A register, and after the break we can inspect this at the memory location F3 on Q1. So if I just go to F3, then we have 12. Now you might be wondering, right? So 10 plus 1 definitely would be 11, not 12. But where this extra 1 comes from, it comes from the carry flag. Hence the name of the instruction, add with carry flag. And that's the reason why before the addition, we usually not always, we usually want to clear the carry flag to make sure that this value is actually going to be 0. So if I just make, so this line represents like some random state, let's say for the carry flag when we encounter in this addition. So before this, we usually do the following thing. So we usually just clear the carry flag and then add. In this case, if I upload and if I assemble and upload and go into 200s and run, so to run I press Shift G. So again, like 200, then space to go there, then Shift G to run. That's how I do it. And now I go to F3 and space, and now we have 11 here, which makes perfect sense because actually 10 plus 1 is indeed 11. So you might be wondering, like, why actually this carry flag is needed at all. So why not just to drop this? And here is an interesting thing. So let's consider if we have the result of the addition that exceeds FF in hexadecimal or 255 in decimal. So for instance, if we have the value of FF here, right, and then I want to add 1. So what would we have as the result? Let's have a look. So remember that we cleared the carry flag here, right? So I want to assemble this one more time and upload and go into 200s and Shift G to execute and F3 to inspect the result. And now we have 0 in the A register. So you might be wondering, why is that happening? Well, that is happening because it just wraps around. So like 255 plus 1 is going to be 0. However, here is an interesting thing. If it wraps around, it tells you this on a hardware level by setting the carry flag. So if we just have a look at F1 here, then you see like it's 3-3. So for instance, we need to make sure that we clear the carry flag before making this addition. So at this time, it was actually like it actually was like it was like, oh my god, 0, right? But after this operation, so we've wrapped around, so the carry flag is set to 1. So at this point we have 3-3, which is 0011, 0011. So we have still this expansion and break flag. We also have the 0 flag being set and the carry flag being set. So you may be wondering, why do we have the 0 flag being set? Well, that's because we've ended up, after this operation, we have ended up with the value of 0 in the A register. So again, like you see, like F3 was equal to 0. So for instance, if you want to add 2, right? Then let's do this assemble and upload and 200s and Shift G and F3. So now we have 1 in the F3, so plus 1 is going to be F turns into 0, and then it starts adding to 0, so 1 more left, so plus 1 is going to be 1, right? And so on. But if we have a look at F1, then you see like it's already 31, which stands for like this. Like actually what we had here as well, because 0 flag is no longer set because this value, the resultant value is not 0, it's actually equal to 1. All right, so hope this makes sense. Now, this simple mechanism of setting up the carry flag in case if the number is wrapping around can actually be used in order to add 16-bit numbers. So let's, for instance, consider the following example. So how do we have the result of this sort of a thing? So for instance, we can do the following thing. So currently, whatever we have in the A register is the lower bit of the 16-bit number. So let's just define two variables. So let's call it result high, and just define a byte there. So DCB, just a placeholder to be able to reference this, and resource low. Okay, and also DCB, and like this. You know, so yeah, probably let's define print byte. It's called print byte, and there is the address one. This is the key monitor specific call to output the hex value as the ASCII characters. So 1E 3B. All right. Yeah. So here currently we have the low in the A. So the low, if here I say, yeah, for instance, I want to say STA to result low. Okay, let's actually start writing some commentaries because it might be getting a little bit complicated. So here I have let's just say ROM routine to print hex number. All right. Here we want to load hexadecimal FF to the accumulator. Here we clear the carry flag. Okay. Here we add 2 with the carry flag. Store accumulator to res L. So this is the lower byte. All right. So now we have our lower byte here, and for instance, want to print lower byte. Okay, so I can say, let's say LZA res L, and jump to subroutine print byte. So here we want to load lower byte to accumulator and want to print it. So it should now print the value of 0, 1. So let's quickly check this out. So if I assemble and upload 200s and Shift G, and indeed we have the 0, 1 being printed, which is the lower byte, which is okay. But what about the higher byte? In this case, we can do the following thing. So for instance, we can say LDA result high. So make sure that this value is equal to 0, which now it is. So result high. And now carry has been set after this operation. So currently carry is equal to 1. So if I just simply say add with carry and the value of 0, this might be seem pointless. However, this would actually add the carry flag to 0, which would result in 1. And then we can store this as the result of our res h. So here, load result h. So high byte equals to 0 to the accumulator. And here, literally add the carry flag. All right, and store result. Store the result in res h, which is the high byte, the higher byte. Yeah. Okay, so also we want to print the high byte. So here I can actually, well, I can't say LDA. I may not. Well, let's even though it's a bit of a redundancy, still let's do this. So say LDA result h, and now jump to subroutine print byte. So here what we did, load higher byte to accumulator and print higher byte and print the higher byte. All right, so now let's assemble and upload and to hundreds, and here we go. So we have 0101. Now if you want to check this out, you can just open the calculator. Let's go into the hexadecimal mode, for instance. And what we did here, we tried to add 02 to FF initially. So we go to the calculator and we say FF plus 02 is indeed equals 101. So this was an example of how to deal with a value. Well, actually this 102 is already a 16-bit value because it occupies 2 bytes in order to store the result. But it doesn't yet answer the question of how to actually add 2 numbers. So now let's consider a little bit different example. So just delete this code here. I don't need this anymore. And let's consider we have the num1 higher bit, num1 h, and dcb0, num1 lower bit, then num2 high and low as well. So here are the placeholders for our numbers. So here, let's for instance we have let's have 1034 for instance, and here we have like, I don't know, like let's say just, I don't know, some whatever random number. Okay, so yeah, probably even better having this value somewhere like let's say FA, to make sure that it actually wraps around as well. Okay, so the first thing we want to do is to add the lower things. So I can say LDA num1 lower, and then I say clear carry flag. And yeah, by the way, even though it's in this simulator it's not absolutely essential, but you obviously need to clear the decimal flag. Clear decimal flag in order to make the add with carry and subtract with carry work properly, like with the actual numbers, not in the decimal mode. It's a little bit different story. So in a decimal mode, if say we want to add 1 to 09, so in hexadecimal mode it would 009 plus 1, it would be 0A. In decimal mode it would be 10, because that's what you would expect in the, if you think that these numbers are decimal. So to avoid that behavior, we want to clear the decimal flag first. So here we want to load lower byte of num1 to the accumulator. Here we want to clear the carry flag. Clear carry flag. All right. And then we want to add with carry num2 lower byte. So we're taking this byte and adding to this byte. And as we can already see, that this would result actually in wrapping around. So after this operation, well, we know for sure that the carry flag would already be set to 1. So now the next step is actually to add these two values, but we are not going to be clearing the carry flag before this addition, because we want to make sure that the wraparound from the low byte addition would also be taken, be considered within this entire operation. So, well, probably first we need to store this as the result low. Okay. So here, add with carry lower byte of num2. Okay, store result into result lower byte. Okay, and now want to say LDA num1 higher bit. Okay, so load higher bit, higher byte, sorry, higher byte into byte of num1 to accumulator. And now without clearing the carry, it's important, it's incredibly important, because otherwise we lost the overlap from this low byte addition. We already do this add with carry and num2 high. So add with carry higher byte of num2, and want to store this result into result high. Okay, store to higher byte of the results. All right, and now print stuff. So let's say LDA, it's actually already there, so we can have not been doing this, but anyways, so let's load the result high, even though it's already in the A register, but anyways, and then we can say jump to subroutine print byte, and then we want to LDA result low and jump to subroutine result print byte. Yeah, this is it. So now let's assemble the code at 200s, upload 200 space shift G, and we have the value of the result of adding this to numbers. So now let's open the calculator and make sure that it's exactly what it should be. So we have 1034 plus 35 FA equals 46 to E, which is exactly the value that we got as the result. So here is how we can add to 16-bit numbers in 6502 assembly. This is it from my side, guys. Thanks for watching. Until the next time, and take care.